All right, everybody. Welcome to BMP Summit session number 2. My name is Vivek Sharma. I'm a state BMP coordinator and a soil fertility specialist in Soil and Water Sciences Department in Gainesville. Dr. Michael Dukes works pretty closely with me, and he's the co-organizer for this BMP Summit. Today we have 2 speakers. Mabry McCray and Vivek Sharma. Mabry will go first, and Mabry will explain about the nitrogen management in agriculture system. The floor is yours, Mabry.
Okay, thank you. I'm Mabry McCray. I'm an agronomist at Everglades Research and Education Center. My topic today is nitrogen management in agriculture. It's a pretty big topic, so I'll try to hit the high points and include some discussions related to BMPs. First, an outline of the presentation. I'm going to center the discussion on the nitrogen cycle, including inputs, components, and losses, potential losses of nitrogen. Nitrogen inputs will include things like manure and biosolids, nitrogen fixation, compost, and plant residues, and commercial fertilizers. And we'll talk a little bit about the 4 R's of nutrient stewardship and the importance of that. And then talk about potential nitrogen losses, including runoff and erosion, volatilization, denitrification, and leaching. And then we'll have a brief summary. So first of all, just to emphasize the point that nitrogen is a primary plant nutrient. We have essential plant nutrients that are categorized either as primary, secondary, or micronutrients. So, and all of those essential nutrients are needed by the plant, but the category that they're placed in is dependent on how much of them the plant needs. Nitrogen is a primary nutrient, so it's needed in large amounts by the plant. And I just got a couple of pictures here to illustrate that from a study a few years ago we had with nitrogen rates on per sugarcane on sand land. These are sand soils, so we had rates from 0 to near 300 pounds of nitrogen per acre per year. And you can see the photograph on the left, the sugarcane was growing very poorly with no nitrogen. We had very, very low harvest weights there without nitrogen. The photograph on the right was with an adequate amount of nitrogen, illustrating that on our sand soils in Florida, on soils in Florida in general, except for the muck soils south of Lake Okeechobee, if you don't apply nitrogen, you won't get much of a crop produced. So emphasizing the point that nitrogen is a primary nutrient and it needs to be supplied to the crop at the right time for that crop in order to produce a successful crop. Looking at the nitrogen cycle in general, the green ovals are the components of nitrogen that are part of that. The blue boxes are inputs to the soil from different components, and the red boxes are potential losses from the soil. So the first we'll talk about some inputs that would include things like nitrogen atmospheric fixation. Well, you do get a small amount of nitrogen that is fixed with lightning. That would be a small amount that we don't have any control amount over. When we also get some inputs from animal manures and biosolids, biological fixation by legumes, and plant residues. And we also have inputs from commercial fertilizers. So the first things that we'll talk about are some of the inputs from animal manures and biosolids, biological fixation by legumes, and plant residues. So looking at animal manures as a nitrogen source, one of the things that's important to remember is that these are basically limited to application near the source. You can't afford to transport these very far because the low analysis of the materials and the heavy weight that you're transporting. They vary in nutrient content by animal species and how the manure is made. The plant available in for the first year after application is the sum of the ammonium and organic nitrogen. Plant available in for the first year of application is the sum of ammonium nitrogen and 25 to 30% of organic nitrogen. So then the second and third years, you would get about generally an average of 12% the second year and 6% of the organic nitrogen available the third year. So you're getting the largest amount of nitrogen available during the first year and reduced amounts of available nitrogen after that from a manure application. You can have large volatilization losses after application, and so soil incorporation can reduce the loss through volatilization. There are regulations regarding animal manure use in some situations, including intervals between application and harvest for some crops, and also the distance of application from nearby water bodies. So in some situations, you have to pay attention to the state regulations regarding the use of animal manures. Biosolids are also a potential nitrogen source. These are products of municipal sewage treatment. These contain organic matter and nutrients, but also contain heavy metals that have to be monitored. You have Class A and Class B biosolids. The Class A biosolids have been treated to reduce pathogens, and these can be applied to all crops, lawns, and gardens. And then you have Class B biosolids that have less rigorous treatment and have restrictions for public access, animal grazing, and crop harvest. So nutrients applied in highest amounts are nitrogen and phosphorus. And so management of these nutrient applications will be similar to those for manures. The U.S. Environmental Protection Agency has established ceiling concentration limits and cumulative pollution loading limits for heavy metals. And so it's important to keep records of application if you apply biosolids that include loading levels of each nutrient and soil test values. So public perception of manure and biosolids applications can sometimes influence a grower's decisions about using these. So that's an important thing to consider before deciding on use of biosolids. Next, symbiotic nitrogen fixation by legumes is another source of nitrogen. The management includes optimization of soil pH and calcium and inoculation with the proper bacteria for the legume species you're growing. The amount of nitrogen fixed is going to vary greatly depending on the species that you're growing, the yield that you get, the effectiveness of the nodulation, and the nitrogen that was previously available in that soil. When legumes are grown in combination with grasses or other crops, nitrogen can be supplied for both crops, but in some cases in Florida, you may need supplemental nitrogen in addition to the legume you're growing. Legumes are sometimes used as cover crops, which provide a number of benefits for the soil, including nitrogen for the next crop. Here's an example of a legume that we see sometimes grown in Florida and South Florida anyway. The sun hemp has been used for the last few years, sometimes as a crop between plantings of sugarcane on sand land. Adds the benefit of some nitrogen for the following sugarcane crop, and also potentially long-term slight increases in organic matter content. Okay, the addition of compost and plant residues to soil is another source of nitrogen. These materials can add organic matter to soils with associated positive effects on cation exchange capacity, water holding capacity, and soil structure. The nutrient content of the compost and residues can vary greatly depending on the source and the quality of the material, though. These materials have a wide range of carbon to nitrogen ratio, and this will influence the availability of soil nitrogen. If you have a CN ratio greater than 30, this will result in immobilization of nitrogen while the microorganisms break down the carbon in the material. After the carbon is broken down, then the nitrogen will be available to the plants again. But during this process, while the nitrogen is tied up, you may need to apply additional nitrogen if you have a crop growing during this period of time. So it's an important thing to remember. If you have CN ratios less than 15, then you can have mineralization of organic nitrogen, which will provide plant available nitrogen. Between those two values, you would tend not to get, between 15 and 30, you would tend not to get net mineralization or immobilization. So this is an example of a trial that we had several years ago. We used a compost sludge material in an application on sandland sugarcane. We applied this at about 60 cubic yards per acre, and we got good benefits. We had an increased sugarcane yield and showed that we could, especially the first year, reduce the nitrogen rate compared to not having any compost applied. So it certainly can have benefits in terms of crop yield and possibly reduced nitrogen from other sources for the first year or two. Okay, commercial nitrogen fertilizers are another source, and they have a wide range of sources to choose from. For dry granular sources, this can include urea, which has the highest in analysis of the dry granular sources. Ammonium nitrate, 33 to 34% nitrogen. Ammonium sulfate at 21. And then a little bit lower calcium nitrate, potassium nitrate. And the phosphorus sources of diammonium phosphate and monoammonium phosphate, you also get some nitrogen. Liquid sources include urea ammonium nitrate from 28 to 32% nitrogen, aqua-ammonium solutions at 33% N, and anhydrous ammonia at 82% nitrogen. Those are all soluble nitrogen sources. The anhydrous ammonia has a high nitrogen analysis. It's a liquid under pressure. It has to be transported in tanks and requires special equipment to inject it in the soil. But in certain crops and certain cropping systems, it's a good choice. Generally, the cost of nitrogen per unit of nitrogen is lower in the higher analysis materials. As I say, the anhydrous ammonia, you have to have special equipment. The urea, 45% nitrogen as a granular source, but it does have the problem of if you apply to the soil surface, you can have a lot of volatilization losses, especially with high pH. I'll talk some more about that later. So those are all soluble sources. You have some slow release and control release nitrogen sources also. So slow release is not the same as control release. Slow release sources include urea formaldehyde, methylene urea, and IBDU. These generally are called slow release, and the release depends on climatic and soil factors. You don't really have control over the release of those materials. The control release nitrogen sources include sulfur-coated urea and polymer-coated fertilizers. And these you would have more control over the release of the material. The polymer-coated fertilizers have become more popular in recent years. These tend to be formulated so they release in terms of in relation to temperature, and they you can plan the release for your crop in terms of when the crop needs the fertilizer, or so with those than the slow release sources. The control release fertilizers are more expensive than soluble, but they you can have formulations that could include soluble and control release. Okay, Okay, so managing the nutrient inputs to reduce nitrogen loss. Then you have the components of nitrogen that include atmospheric nitrogen that's not available as that to the crop. You have organic nitrogen. You have ammonium, which is a cation, which can be held by the negatively charged soil particles. You have nitrate, which is negatively charged, which is not going to be held by the soil. It's going to be very mobile in the soil and leach. And so then the potential losses then are going to include volatilization, runoff and erosion, denitrification, and leaching. What you want to try to do is get as much of the nitrogen that's applied actually in the crop and going into the crop harvest. So it's a good time to stop and talk about 4 R's of nutrient stewardship and the importance of them. First, the right source. Match the fertilizer type to the crop needs. This might be whether it's granular or liquid. It might be soluble fertilizer versus control release, but the source that's appropriate for your crop and your cropping system. The right rate, the amount of fertilizer matched to the crop needs. You should pay attention to recommendations in the nutrient response curves that have been developed for your crop in your area that would tell you how much nitrogen do you need for that crop. The right timing of the application. This might include split applications, so they're available when the crop needs it, or control release in some situations. The right placement of the nutrients. In some cases, this might be injecting it into the soil. It might be a banding application, but the placement so the crop can use the nutrients as best they need to. Reducing nutrient loss from runoff and erosion. So this is one potential loss is when you lose soil, you lose nutrients. There are BMPs for reducing soil loss and erosion that are specific for region and the cropping system, and should pay attention to those that are specific for your situation. In some cropping systems, there can be perimeter borders used to reduce soil loss from wind or water erosion. These borders can be either vegetation or synthetic barriers. In the Everglades ag area, we have sediment control BMPs that include leveling fields, ditch and canal bank berms, and use of cover crops to reduce soil and nutrients. And that system is not designed primarily for loss of phosphorus, but those kind of BMPs can also be important for nitrogen. Whenever there's soil erosion, there's nutrient loss. And so that means that you're also losing organic matter, cation exchange capacity, and crop productivity, in addition to the impact on water quality. So it's an example of a vegetative border that's planted, reducing especially wind erosion, preventing the soil particles from impacting the crop. Okay, another potential loss is volatilization. This occurs when ammonia gas is lost to the atmosphere. In terms of commercial fertilizers, it's especially a concern when the urea, which is 45% N, is applied to the soil surface. Also, the urea and UAN solution reacts the same as dry urea, so it has the same concern. Also, other ammonium fertilizers can have substantial volatilization when you have high pH conditions. There can be large volatilization losses from manures and other organic amendments. And this is more of a problem in high pH soils because the high pH results in the conversion of the ammonium cation to NH3 gas. So you can have large volatilization losses in pastures and in turf grass, where you wouldn't have the opportunity to incorporate the material. And ammonium volatilization can also be a problem when you apply anhydrous ammonia into high pH soils or coarse sand. So that might be a situation when anhydrous ammonia would not be the best choice. So to reduce volatilization losses, some things that you can do incorporate the urea or ammonium fertilizer as if possible when you're applying uncoated urea. You also may consider sources other than straight urea as a nitrogen source. When you're applying urea to turf grass, you can irrigate soon after application. Also, urease inhibitors. Urease is an enzyme that promotes the conversion to ammonium and to the loss of nitrogen. And so you can apply urease inhibitors that will inhibit the first step in this conversion. But the downside is this delay can only last for typically 7 to 14 days. So it's a fairly short-term loss. And so during that time, you would need to either get rain or irrigation or incorporation to keep from having the losses. Coated urea can also be used as a control release source, which prevent volatilization, but it's of course more expensive than uncoated urea. Nitrification is an important conversion, which is converting the ammonium cation to nitrate. It's a two-step process, to nitrite and then to nitrate. It's a microbial enzymatic oxidation, so it's carried out by either bacteria or archaea in the soil. And the temperatures that are most favorable for nitrification are from 80 to 90 degrees Fahrenheit. So in warm, well-aerated soils with adequate moisture, nitrification is carried out very rapidly. And so under Florida conditions, the ammonium will be converted to nitrate in a short period of time. So then it's in the nitrate form, it's a negative ion, so it's potentially lost to leaching. It's very, very mobile, especially in our sands. So we also have the option here of a chemical nitrification inhibitors that can delay this process and might be applicable in some situations. But it's important to keep in mind that high temperatures will reduce the duration of this delay with these inhibitors. So you have to look at that and look at the economics in your situation if that's an option. So denitrification then is a potential loss of nitrogen in the gaseous form, either as nitrous oxide N2O or into nitrogen gas. So denitrification is more of a problem in poorly drained soils, but can occur in any soil with flooding or when the water table is high. So this is a problem when you're in wet conditions, when the soil is anaerobic. The process results in the loss of available soil nitrogen to the atmosphere. So, and then if you're losing nitrous oxide, that's a greenhouse gas, so that's an additional concern that it's not good. So to minimize denitrification, you need to use practices that promote good drainage and also avoid large applications of soluble nitrogen where you have a lot of nitrogen that's available for the denitrification. So then leaching loss of nitrogen is another potential loss from the soil. Leaching is the downward transport of soluble nutrients in the soil. Nitrate is mobile in the soil because of its negative charge. So it's not held to negatively charged soil particles. Ammonium is quickly converted to nitrate through nitrification with warm temperatures. So in Florida, in our warm temperatures and high rainfall, the potential for leaching of nitrate is great in our area. So to avoid excessive leaching of nitrogen, we need to avoid large applications of soluble nitrogen, including ammonium and nitrate sources. It's important to split applications of soluble nitrogen through the growing season to supply nitrogen when needed by the crop. So then also, if available, using fertigation is something to consider to supply some nitrogen through the irrigation system. Another option is control release fertilizer to reduce leaching losses. Control release fertilizers generally use a polymer coating that's dependent on temperature for release of nutrients, with faster release at higher temperatures. If it's dependent on temperature, then if you get a heavy rain, then that's not causing the release of the nitrogen. So that's one of the reasons these have become more popular in recent years. Nitrogen nutrient release will depend on the type and the thickness of the coating. By combining soluble nutrients with coated materials with different release times, you can formulate a material to match your crop nutrient demand within a growing season. Control release fertilizer is more expensive, but you can eliminate some application costs with fewer number of applications. Control release fertilizer has the advantages of supplying nutrients as a crop needs them and having less nitrate and nitrogen in soluble form in case of high rainfall. So in a lot of cases, you may not, you wouldn't necessarily have to apply this as just one application during the year. You might apply a blend of soluble and control release that last time that you can get in the field with ground equipment. And when using a control release material, it's important to look at studies confirming the quality of the material and the timing of the nutrient release. There can be a lot of differences in quality, and it's really important to pay attention and look for studies that show the quality of the material and the release times that you're buying. This is an example of our nitrogen recommendations for sandland sugarcane that we updated these about 5 years ago. And basically this is for plant cane. This is the first year crop. The recommendation is to apply 220 pounds of nitrogen per acre per year in 5 splits if it's an all soluble program. For ratoon crops, second year and beyond would be 200 pounds in 4 splits. So an important part of that, the BMP, is that you wouldn't be applying more than 50 pounds of soluble N per acre in each split application. And for sugarcane in South Florida, typically these last 2 applications we have to fly on because the cane's too big to get into the field. So in a lot of cases, growers have went to in part a control release program where they can eliminate the aerial applications and reduce the number of applications to 2 or 3 with a combined soluble control release program. Aerial applications are not an option for a lot of folks and with other crops, but as I say, you might consider that last application with ground equipment, including control release, rather than having an application that includes a high rate of soluble nitrogen. There's also a rainfall exception, which we included when we get a period of heavy rainfall that would allow growers to put an additional 30 pounds of nitrogen. So in summary, it's important to remember that nitrogen is a primary nutrient, meaning that it's needed in large amounts by the crop. And so it's important to put it out there and have it available for the crop when it needs it. Nitrogen sources include organic amendments, nitrogen fixation by legumes, and commercial fertilizers. Organic amendments are an alternative near the source, and incorporation reduces the volatilization losses from ammonium. When adding compost or plant residues, pay attention to the carbon-nitrogen ratio and possible immobilization of nitrogen during that period, and you might need to apply some extra nitrogen if you have a high C/N ratio that you're applying. When you're applying straight urea, irrigate or mix with soil soon after application if possible. And I'll put this in bold because I think this is really important in terms of BMPs. Avoid large applications of soluble nitrogen, preferably applying less than or equal to 60 pounds per acre per application. That's where you think about your split applications and timing of when the crop needs it. To reduce leaching losses of nitrogen, split the applications and use fertigation if available. And then also consider control release fertilizer as part of the program. And like I say, you may not need to apply all of this is only one application per year. You might just include that last application as a mix of control release and soluble. And it's important to remember the 4 R's: the source, rate, timing, and placement of the fertilizer is really important in terms of planning your nutrient management program. Thanks. I'll be glad to try to answer your questions.
Hi, Mabry. Thank you for your presentation. If there is any question, please raise your hand or type your question in the chat box. There is one comment, I believe. I can read it for you. In Florida, our agriculture operations need a permit from FDEP in order to be able to land apply Class A or Class B biosolids. Is that the case?
I would have to check with DEP on that. That may be. I would think that, you know, it wouldn't be a problem to apply Class A biosolids, but Class B might be more of a concern. But I would check with DEP or FDACS about the specific regulations, and it's going to probably vary depending on what crop you're growing.
All right. The second question is pretty long, so bear with me. In your slide, you have used animal manure as a source of nitrogen and stated that plant available nitrogen could be estimated by sum of ammonium and 25 to 30% of organic N. I think there is a nitrate as well. Can you please share the method you use to determine this approach to an estimate and a description of the soil type and condition that this is most likely to be accurate? In some Florida soils, I would expect a little more from the organic nitrogen fraction, but of course that depends on management also. Thanks, Daniel Treadwell.
Well, that's where those are general rules, general guidelines, and that's where you probably would, if you're going to use manures, you should probably get an actual analysis of the material you're using and to see how much nitrogen you're applying and to get a better estimate. Those are general guidelines in terms of how much you could expect to get that first year. Whatever's in the ammonium form, you're probably going to get, plus that percentage of the organic is going to mineralize. It may be, you may get a higher percent in Florida that first year because of our high temperatures. But generally, you're going to get the biggest amount of it available that first year and succeedingly less the second and third years. So those are general guidelines, but getting an analysis of the material will help you with that.
I have a follow-up question, Mabry. When somebody is getting a compost or a material from a client, is it something the client provides that analysis with the product, or is it something the customer has to do by itself, a lab analysis?
Well, that probably depends on the specific situation and whether it's available. I would say that I would ask the question, and if they have it, then that's good. If not, then maybe they could request it or get it done themselves. But if you're using very, very large amounts of this, I think an analysis is really important, because these things tend, because the difference in the material that they're from and the quality, they can vary all over the place in terms of the analysis you're actually getting.
So if besides the nutrient analysis, it's also important to get the CN ratio right too, right? Otherwise it will actually hurt rather than give you benefit applying this on a crop.
Well, that's really important to consider that before you go with a particular compost or material. You know, doesn't mean you might not necessarily use it, but it might affect the timing of application before you plant again, and whether you need to add extra nitrogen.
Thank you. All right. I do not see any additional question in the chat box, but there could be a question at the end of the session. So if you please, stay tuned until the end of the session. That'll be great. Thank you again for your presentation and answering all the questions.
Thanks.
Our next speaker is Vivek Sharma. Vivek is an irrigation specialist, irrigation precision ag specialist. Let me correct myself. In ABE department, housed in Gainesville. Vivek started this position, I think, start of the pandemic, 2020 January. So I'm not sure how many people have get a chance to introduce to him, but welcome Vivek for this BMP Summit, and thank you for agreeing to present today. The floor is yours.
Thank you, Lakesh. Can you see my screen?
Yes, I can.
Can you hear me also? Okay, perfect. Thank you so much for the introduction and the opportunity to speak at this event. Hello, everyone. My name is Vivek. I'm a precision water management specialist in Ag and Bioengineering department at the University of Florida. So in this presentation, I'll talk about application of variable rate irrigation as a tool for precision agriculture. So how I outline this presentation, I'll talk briefly, give you a short, brief introduction on irrigation development, followed by why precision irrigation is important in context of Florida agriculture. What is precision irrigation management? What are the components of precision irrigation management? And then I'll talk about variable rate irrigation, followed by a case study on VRI. So let's start. Historically, we have seen 3 irrigation revolutions we called as blue revolutions. First happened back in 1800 and 1900s with the rapid expansion of irrigated agriculture, when we diverted water from big rivers to canals, to sub-canals to irrigate our crops. The second revolution happened back in 1950s with the introduction of pumps and engines, which allow us to extract groundwater and use for irrigation. And this is the same time we have seen significant increase in sprinkler irrigation with the introduction of center pivot irrigation system back in 1970s. And the present era is the era of precision irrigation, in which we don't have just the sophisticated irrigation systems, but at the same time, we have latest technology, better decision support system, information and networking solutions, communication solutions, so that we can precisely manage water at a very precise scale at a very high resolution. So, we are talking this precision agriculture, from last like a decade or so, but why it is important in context of Florida agriculture. So Florida is, have a very diverse agriculture system and produce very high specialty crops, which highly dependent on irrigation. But if you look on the water side, we irrigate about 1.3 million acres every year. And from the last 2 decades, we have seen about approximately 25% increase in irrigated acres in the state of Florida. And this increase is very variable in different regions in the Florida. This map is showing you the expected increase in the irrigated acres in next 20 years. This document is released by FDAC a couple of years ago. And there are certain regions in the state of Florida where we see approximately greater than 75% increase in irrigated acres, which is equivalent to about 8% increase in irrigated water use. I highlighted this area in which the average expected increase about 30 to 47%, 40%. And this is also the area where most of the center pivot irrigation system is, concentrated on the upper Floridan aquifer. And over the years, with the intense agriculture practices, we have seen increasing nitrate nitrogen concentration in the upper Floridan aquifer. From the last decade or so, we have seen significant adoption of BMPs to control this nitrate leaching. One of the BMP is the irrigation management. And in this presentation, we'll talk about the precision irrigation management. So let me talk with you, what is precision irrigation management? So the main aim of precision irrigation management is to develop a decision support tool in which we include all the data source, that is the climate data source, water quantity and quality data source, soil variability, irrigation system data, so that we can use this data source to optimize our output. And output can be your yield quality and quality, yield quantity and quality, or either reduced environmental footprint by minimizing our input. So input can be any source of input, right? For example, water use. And if I talk just alone, irrigation component, water, and energy are the two basic inputs. But irrigation is not a standalone component in Florida. There are other components that tie along with irrigation, nutrient input. So all those with the decision support system or the tool, we can allow all those components to integrate together to maximize our output. So, many people, I talk with many people, and we are following this principle from last like 3 decades now, But, if you look at the old definition of precision irrigation management, we also call that as an irrigation scheduling. We will concentrate on 2 parts, when to irrigate our crop or how much to irrigate, turn on the system, turn off the system. These are the 2 essential components. So what we are adding new is the spatial component, where to irrigate within the field itself too. So the spatial dimension of water management has changed the definition. So what the current definition of precision management is: accurate and precise application of water to meet the specific requirement of individual plant or management unit. So there can be a set of variabilities that can be associated in the field. For example, this graph or this picture is showing you the variation of soil type in one field. For example, sand and clay loam have a different water holding capacities, So we can apply water variably within the field to increase the productivity. Okay, so why precision irrigation management? As I talked, both insufficient irrigation and extra irrigation can harm your product, overall productivity. So precision irrigation management allow us to optimize our yield quantity as well as the quality of the produce. The most important I can say is increase the water use efficiency, reduce pumping and energy cost. And in Florida, as I mentioned before, irrigation and nutrient application are so tied together. So by optimizing the irrigation, we are also optimizing the nutrient application, in which we are reducing the nutrient loss from the field, either by runoff or by nutrient leaching, which can reduce the environmental footprint. So now I'll talk different components of precision irrigation management. There are basically 3 components of precision irrigation. One is in-field sensing, in which you use a set of sensors. Either it can be a soil moisture sensor, canopy temperature sensors, or we can use other advanced tools like satellite imagery or drones, or we can sense a certain property of a plant or a soil to make a decision. So once we have this data, the next component is the decision making. Decision making, in which we use various models or algorithms to make a decision based upon the data that we collected. And the third component is the field operation, in which we transfer the decision to the irrigation system so that it can apply water, at right amount, right time, and at right location. So these are the 3 components of the precision irrigation management. And when we integrate all those components together to make a decision support system is the aim of the precision irrigation management, in which we have sensing mechanism from the field. We deliver that sensing mechanism into models or into artificial intelligence tools. And then we can transfer those decisions into the irrigation system to apply water. And from last 1 year or so, we have seen, or we have heard here, a lot of talks on IoTs, artificial intelligence or machine learning mechanism. We can introduce those things into the decision-making process so that we can reduce the amount of data that we collected from the field also. So one system that integrates all the 3 elements of precision irrigation management is the variable rate irrigation system. So variable rate is also known as the site-specific irrigation management, or VRI. The basic assumption of variable rate is that irrigation requirement may vary spatially within a given field. So we can apply water variably into different areas or individual management zones. I think the key term here is the management zone. And based upon those management zones, we can develop based upon the observed condition. For example, this map on the left-hand side is showing the spatial variability of a certain property. Let's say soil moisture. in the field. And based upon that soil moisture variability, we developed the prescription map that we feed into the irrigation system so that system can apply water variability. All those colors here on the right side is showing the different depths of irrigation. For example, let's assume that blue color is showing you the 100% irrigation. So we apply 100% of irrigation, and the yellow and orange color is showing you the reduction in the irrigation. So let's say 30% reduction in the irrigation system, irrigation depth that we apply. So this is how the basic framework of variable rate irrigation system looks like. As I said, we need to sense certain property, of a crop or the soil to make the informed decision or to make the management zones. And there are various tools that are available in the market. For example, soil moisture sensors. There are tons of soil moisture sensors now available in the market, which can measure the soil moisture or volumetric water content of the soil at different depths, which can be used to make the management zones. Other would be canopy temperature. Once your crop is mature or it's covered the ground, then we can use the infrared IRTs or infrared thermometers to collect the canopy temperature, which can at multiple locations at the field, and we can feed that information to make the management zones. The other is the drone or satellite imagery. We can use those imageries to sense a property, for example, NDVI or leaf area index or crop evapotranspiration, and then we can use that map as a source of input for the variable rate irrigation management zones. But these properties or these instrumentation we can use throughout the growing season, but there are some prerequisite conditions where also allow us to use the variable rate irrigation system. Some of the variation in the field, for example, topography, you have irregular fish, you have low spots in the field, you have, if somebody is growing multiple crops under the same pivot or the same irrigation system, there is a non-crop area in the field, or there is an overlapping pivots, or there may be a difference or variability in the soil physical and chemical properties. So let me illustrate you all those by images. For example, this image clearly defining a low-lying spot in the field, and the water is standing over the field. We don't want to irrigate that particular part of the field. So variable rate irrigation system allow us to switch off those nozzles when this area comes in, and we can irrigate rest of the field as usual. The other condition might be multiple crops. If multiple crops are grown under the same pivot or the same irrigation system, for example, one half in Florida situation, for example, one half of the pivot is corn and the other half is peanut. Both have a different irrigation requirement and a different growth stage. So variable rate irrigation system allow us to change the prescription based upon the crops also. Other is the non-crop area. For example, if you have a ditch running from the field, or if there is a pond in the middle of the field over the over the sprinkler under the sprinkler irrigation system. So variable rate irrigation system allow us to switch off the nozzles when that area comes in, so that we can irrigate the rest of the crop as usual. The most important, there is another one is the overlapping pivots. So this is an aerial screenshot of an area with the yellow circles is representing the irrigated area using the pivots. And you can see all the red boxes is the overlapping areas, and in general, we don't want to irrigate that overlapping areas multiple times. So variable rate irrigation system also allow you to switch off the irrigations when those overlapping areas comes. And the most important is the soil variability. I showed you this map before also. For example, this field is showing you the variability of soil within the same field, right? And if you go back to the basics, sand, which have a low water holding capacity compared to clay, which can hold the water for a longer duration. So variable rate irrigation system allow us to irrigate crop variably throughout the growing season based upon those variations also. Okay, okay, we decided the condition, okay, we need variable rate irrigation system in our field. So what are the systems, what kind of systems are available in the market? There are two types of variable rate systems are available. One is called the sector or speed control. The basic idea of this system is to speed up or slow down the pivot so that you can design the application depth. For example, if you slow down the system, that system is staying for a longer duration at a particular area, applying more water, compared to when you speed up the system is staying at for less time on that area, applying less amount of water. The other type of system is called the zone control system. So in zone control system, we have an ability to control the water applications of an individual zone. For example, in this figure, each rectangular section here, small section is representing a different zone. So we can variably apply water for each section. And this can be very handy if we have a significant variation within the field. There is another type of variable rate irrigation system mostly used for research purposes called individual sprinkler control system, which we categorize under zone control, in which, so in a typical zone control system, your 5 to 6 nozzles, I can say your 5 to 6 nozzles are applying the same amount of water, and the next 5 to 6 nozzles, you can variably apply the water. But in individual sprinkler control system, you have ability to control the volume of water coming out from the nozzles from each sprinkler. So that's mostly used for the research purposes compared to any production setting. Okay, so if you look at the, as I mentioned you before, the basic foundation of VRI technology lies in the development of those management zones or the prescription maps, right? So there are two types of prescription maps also that we can establish using the variable rate irrigation system. One is the static prescription map. So static prescription map is you sample your field, for example, before the crop, before the planting. For example, you looked at the EC mapping using a various, or you did a grid soil sampling and you assess a certain property of a soil, or you looked at the historical yield data from last 5 years, and what are the low yielding spots, what are the high yielding spots. And based upon that, you develop a management zone and you fed into the sprinkler system. And your sprinkler system apply the amount of water based upon that management or based upon that prescription map throughout the growing season. So irrespective of changes that happen within the growing season, it doesn't take into account for. So the static prescription map stays same throughout the growing season. The other is the dynamic prescription map, in which you sense the property of a crop or a soil throughout the growing season at regular intervals. And based upon that property, you prepare the prescription map and then feed into the irrigation system so that your variable rate irrigation is, have a temporal scale also. So you are variably applying water throughout the growing season as well as spatially. So again, the question rises here, you can see this picture. There are three sets of sensors in here. And in this field, we installed almost like 20 different sensors. But practically, this is not possible. Research purposes, yes, this is, we can do that. But if we look at the production scale on a producer scale, financially or economically, this is not possible also. So now what are the other alternatives that we can use to develop the dynamic prescription maps? So one is the use of remote sensing. We have the accessibility of drones or high resolution satellite imageries also. We can use those using various models to develop a prescription or to sense the variability throughout the growing season. For example, this 7 maps is showing you the variation of leaf area index, NDVI, as well as crop evapotranspiration throughout the growing season. This is for the alfalfa crop. And you can see with proper tools, we can assess the variability very precisely. For example, right around third map, you can see there's a drastic change. And if you look at the alfalfa practice, alfalfa has a regular cuts, So right around this, we have the harvest alfalfa. And you can see the LAI and DVI reduced significantly, as well as the evapotranspiration, which can be used as a source of prescription map. The other is the use of other advanced technologies. For example, integrating the sensing mechanism within the irrigation system. For example, this is showing you, sorry for the dark image, but this is showing you the canopy temperature sensor installed on the pivot so that it can sense the canopy temperature when the pivot is moving itself. So, but over the years, from the last decade, I can say a lot of research happened on that, and generally those instrumentations are used to collect the canopy temperature data at one particular point, again on a rotating event. So there is an average area, and you will get an approximately average value of canopy temperature from that area. But what we are going toward is the thermal map. If we can install the thermal camera on the pivot itself, and how we can then sense or prepare a map of canopy temperature, in which we can see the variation of canopy temperature over the growing season. This is kind of a research has been done, my colleagues in Bushland, Texas, where they use the thermal camera to assess the canopy temperature over the growing season. Again, so this is the nutshell, the mechanism that we use in the variable rate irrigation system. So you develop the prescription map, either based upon soil moisture data, either use the remote sensing tools, and you input that variable prescription map into the irrigation system. This is the variable rate irrigation map that you develop based upon these properties, and you input that into the variable system. And then there are variable rate units installed on the system that can apply water by using the pulse control. The pulse control is the on and off of the system. So for example, if you are applying 100% of water, so there would be a constant supply of water compared to when you're applying, say, 80% of water. So there is an off time when there is no water applying, and then they start again. So that the timing of off switch depending upon the amount of prescription that you provided. One system that include or being developed or being used for variable rate irrigation is called the SCADA system, developed by Bushland, Texas, in collaboration with the Valley Walmart Industries, in which what they integrated the weather data, canopy temperature data, as well as soil moisture data into the centralized data acquisition control system, which developed the prescription map and then feed into the irrigation system to apply the water variably. But again, as this system looked very cool and sophisticated, but there are many hidden pieces or missing pieces in the system. But before I go, what's missing and what we need to do, let's talk about a little bit on the economics. So your average variable rate irrigation system, just the variable rate irrigation unit, cost around variable, from $2,500, it can go up to $40,000 also, depending upon your system and the amount of area you are covering, or whether you are going for a speed control compared to the zone control system. So suppose the average cost of irrigation per acre inch is about $10, and you are irrigating about 1,000 acres, that's, account for about $100,000. And by using the variable rate irrigation system, if we assume that 10% of your land doesn't require irrigation, or you save 10% of water, then it's a potential saving of about $10,000, and I believe it's a significant saving. And there are a lot of cost share programs, like for example in Florida, NRCS have equip programs, as well as various water management districts have the cost share programs to for the variable rate irrigation system that producers can take benefit of that. So let me go back to the missing puzzle of the VRI. I call it as a VRI puzzle. We have seen there is a system developed to control the to develop the prescription map and the feed into the irrigation system, but this still decision support system, there's a lack in the decision support system to address the temporal variability. From the sensor, you collect the data, you process that data into the decision making, and then you feed into the irrigation system. So there is a lot of lag time, so how we can address that. Other is most of the variable rate irrigation studies have done taking irrigation as standalone component, but as I said before, irrigation and nutrient management go side by side, So, and in Florida situation, where a lot of people do fertigate, there is enough potential where we can use variable rate irrigation system to apply water as well as nutrient variably across the field. Other is there is not much research on the crop modeling approaches using with the integration of VRI technology. One of the system, on the go irrigation management, we are working on that side now. If we can reduce the lag time between the sensor communication to the transferability to the control panel so that it can be on the go system. The most important, I think, from the last like 10, 20 years we are seeing is the cost. Cost is the big hurdle in adopting those variable rate irrigation system. And there is additional cost of sensing, sensing technology. Either you use a soil moisture sensor, canopy temperature. Can we use some low-cost sensors that we can integrate with the pivot itself or irrigation system, or we produce a low-cost UAV images so that we can reduce the overall cost of the system. The other is the on-farm versus whole field research. Most of the VRA research that has been done is on the experiment stations where we have very controlled conditions, small plots, but the dynamic change when we consider as whole field research. There are a lot of other factors play an important role, and the system get complex under the whole farm research. So I think most of the research efforts should be focused on the whole field research rather than experimental plots. So now I'll talk about one case study that's VRI management that I conducted back in my previous institute at University of Wyoming, in which we installed a brand new half circle pivot that has the capability of applying water variably. These orange lines in here, you can see this web soil survey, very traditional approach, and you can see there are two different soil types. That is the garland silt loam and it's a silty clay loam, Stutzman silty clay loam. But when we did the extensive soil sampling, we saw a significant variation of soil within the study area. We did soil sampling at multiple locations, and we then saw the physical properties of the soil, and you can see significant variation of clay, sand, and silt, and that's not as same as the NRCS web soil survey map. So based upon this grid soil sampling, we developed 3 zones. Zone 1 is the silty clay loam, zone 2 sandy loam, and zone 3 would be loam. And in each zone, we had 2 irrigation treatments. One is the variable rate based upon the soil moisture data. And second is the fixed irrigation, as we do generally. And you can see those irrigation treatments and the location of the plots. These 4 maps is the water holding capacity, as well as field capacity and permanent wilting point spatial variability map based upon the soil properties, which you can see a significant variation within the field itself too. So let's look at the results. So what we did, we used our, let me go back. We used our soil water holding map as the static map at the beginning of the growing season, and we apply irrigation up to like so this study was done for the barley. So for proper emergence, we use water holding capacity map as a mean for static prescription map. But once it get emerged, we use soil moisture data from the network of soil moisture sensors that we have in the field to develop the dynamic prescription map. So based upon that, what we saw is this is synthesized results of that. On the y-axis, we have yield. On the secondary y-axis, we have irrigation amount of applied for different zones. And on the x-axis, we have fixed rate or the variable rate irrigation management. And you can see we have seen significant variation in the water applications, but as well as crop water productivity, how much water being used to produce a certain amount of the crop. And this overall saving is about 23% by using the variable rate irrigation system. We are planning to develop a similar kind of research at Florida, where we are starting at North Florida Research and Extension Center at Live Oak. The idea is to evaluate the effectiveness of precision irrigation technologies like VRI management in using canopy temperature as well as soil temperature for in-season irrigation management. Recently, last week, we did a lot of soil sampling and various EC mapping that shows the variability of soil, like electrical conductivity on the left map. And on the right map, we have the organic matter variability within the field that allow us to select various maps, various zones within the field. And in this particular project, we are going with the 4 treatments in which we have a variable rate irrigation dynamic prescription map based upon the soil moisture or canopy temperature, variable rate irrigation static prescription maps based upon the EC mapping that we just conducted before the planting, and uniform irrigation and rain fed. So we will see the effectiveness of those treatments at North Florida Research and Extension Center at Live Oak. So these are some of the references that may help you to understand this information. I'll suggest you to see this video that really help us to understand the impact of that variable rate irrigation system. This is very synthesized 3-minute video and helpful to understand the process. And with this, thank you so much for your attention, and I'm happy to take any questions.
Thank you, Dr. Sharma, for this amazing presentation. I would say our audience, if you have any question, please type your question in the chat box, and I will repeat that question to our audience and ask that to Dr. Sharma. All right, so we have a very small 40-second survey questions. The link is in the chat box. Emily has typed that. Thank you, Emily. Could you please also give us the QR code for the CCA credits? Emily, here we go. Thank you, Emily. With that, if anybody has any questions, please ask those questions in the chat box. Also fill that survey. The survey is very small. It's less than 1 minute. It will help us to improve our BMP Summit for the future, as well as get some information for our agents and for us to move forward on some of the practices, BMP practices that we are working on. Please feel free to reach out to me if you need any help in adoption of any BMP. Or Dr. Vivek or McCray for any question related to BMP. All right. So Vivek, I have a question for you. When you are using this variable rate equipment for, as you said, it's on the expensive side. Is there any benefit of using it in terms of saving not just water, but obviously the electricity to pump that amount of water? Have you or somebody has done any economic analysis on that? How much? I mean, how quickly you can pay off that $100,000 or whatever the cost is?
Yes, I mean, definitely, this is the most difficult question that always we get on the economic side. There has been some studies on the energy consumption. One of the limitations right now, I talked about on-the-go sensing, So what's happening right now is how the prescription maps were developed is running the system without irrigation by the sensors to sense the property and then run again to deliver the irrigation. So there is 2 times you are running the system, but that's not economically as benefited as mentioned because of the energy consumption, right? So definitely there is additional cost, but at the same time, there is precision also, you get involved in that. But I think most of those can overcome when you integrate those systems. A lot of research now happening on installing the sensing mechanism on the pivot, right? But if we can integrate it with other disciplines like fertility management, on-the-go fertility management or weed identification, if you can, because we are getting the high resolution imagery anyhow from those sensors, but can we use that with other applications or not, so that we can offset the cost? That can be another potential, thing that we can do with the system. But yeah, I totally concur with that.
So the image, sorry, I have a follow-up question on that. So the UAV imagery that you said could be used, is it the crop, the data taken from the crop or data taken from the soil itself?
I mean, it depends, at what stage. Once you get into when the crop cover is full, yeah, definitely we are getting the crop characteristics like NDVI or LAI or even the canopy temperature, so we can feed that information. But with all the tools we have right now, we can definitely, differentiate between the crop and the soil. So that can be another, I mean, there are a lot of tools available. So differentiate those components, and we can feed only the only information related to crop.
Okay, thank you. Yeah, because there are some free services from USDA available now that you can use NDVI for multiple purposes, and this could be one of them. So, all right. So I would request our audience one more time to go over in the chat box and click on the link for the survey to fill out that survey. This is less than 1 minute survey for us, but it will help us a lot in terms of improving our programming in the future. With that, if anybody has any question, please reach out to me. Daniel has commented, great presentation. Thank you, Daniel. And we have next Tuesday, our third session. And I think Emily would also send an email with the CCA credits that somebody wants it. Thank you, Mabry, for your presentation earlier. If I would have any question that I'll receive from the audience, I'll share with both of you for answering that. But I'll also share with you the survey outcomes that I would receive. With that, thank you, Emily, for helping us in organizing this summit session today. Thank you, our audience, for your presence, and thank you, Dr. Dukes, for your help in organizing this BMP Summit. With that, I would say thank you very much, and the session is adjourned.
Thank you.
See you next week.